Alrighty, good morning everybody. Welcome back to non-Euclidean geometry. Plan for today is we are going to continue our discussion of instance geometry and potentially finish this packet today. We will see. As far as office hours go, the next office hours are on Monday after class from 2 to 3. I'll be around a little bit while it's after class today if you want to talk about some stuff. And as far as homework goes, I posted yesterday another homework set, homework 3, that will be due next Friday. And we are also going to have a quiz on Monday over instance geometry. Give you a sneak peek for the future. Once we finish up this packet, we're going to move on from instance axioms to the betweenness axioms and throw in some new Hilbert's new axioms into the mix that are going to allow us to do a little bit more with our geometric model for development. Any questions or comments before we get started for today? What is the only cure for a bad case of the right angles? The only cure for a bad case of the right angles is the Pythagorean theorem. Okay, so just as a reminder of where we left off last time, we still have our same instance axioms that we've been working with for a few classes now. Axiom 1 is Euclid's first postulate that if you have two distinct points P and Q, there exists a unique line incident with both. Instance axiom 2 says every line has to have at least 2 points incident with it. And instance axiom 3 says there exist 3 non-collinear points Q and R somewhere in space. And the models that we looked at, remember a model for, say, the instance axioms is just a way of defining these terms, points, lines, and incidents, in a way that causes the axioms, instance axioms, to all be satisfied. We've seen 3 different models so far for the instance axioms. The first is the traditional model of points and lines that you're used to thinking about in Euclidean geometry. Second model was we talked about last class, which was there are 3 points in all of existence, which are the letters A, B, and C, and lines were sets containing exactly 2 of those points. And the third model, which we also saw last class, is same as model 2 basically, except we have 4 letters instead of 3. So the goal for today is to kind of talk about what does it mean for 2 models of geometry to behave, to be mathematically the same, be isomorphic to each other, in other words. For those of you taken in, say, another math class where that term has come up. So to start with, I'm going to define one more model for us to look at. And this new model is going to be model 4. Here's how we're going to define it. Our lines, I'm going to define lines first, is going to be any one of 3 letters, A, B, and C. We've got, yes, now these are lines, not points. Our points are going to be sets with exactly 2 of these letters in them. And incidents, we're going to say that a point P is going to be incident to a line L if the letter that makes up our line L is an element of the point consisting of the set with 2 letters in it. In fact, last class's examples were counterintuitive all the way. Let's take a look at this. So, Jack, how many points are we going to have in this model?
How many points? 3.
Can you name?
Point AB, point AC, and point BC.
Yes. So I'm going to say point 1 will be the set containing A and B. You're going to have point 2 being the set containing A and C. And point 3 will be the set containing B and C. And if we want to label our lines, we can. We can say L1 is going to have be A, L2 is going to be B, and L3 is going to be C. Question. Is P2 going to be incident to L2? In other words, is point 2 going to lie on our line L2 in this case? Jerry?
No.
Why not?
B is not an element of the set A, C.
Indeed. Yeah. We could say no as our L2 equals B is not an element of the set P2, which consists of A and C. So the questions of incidence now becomes, is the letter consisting of the line going to be an element of the point? Which is kind of the opposite of how the way we thought about incidence with models 2 and 3 from last class. Steph, can you give me a point that is incident to L2? Why's that? Aha! Well, so P.1 is incident to L2 because B is in this set. Any other points that are incident to L2?
Yeah, point 3.
Let's see, because B is in this set. Let's go through really quick just to make sure we agree that the incidence axioms are being satisfied here. Let's see. Is it going to be the case that if we're given 2 distinct points, meaning 2 distinct 2-element sets here, that there's going to exist a unique line that's incident with both? Meaning given any 2 of these 2-point sets, is there going to be a unique letter that's in those 2 sets? Okay?
Yes.
Okay? Let's say we have P1 and P3. What's our unique line that's incident with P1 and P3?
B, 1, 2.
Aha! Because B is the common letter that's in these 2 sets. So in other words, incidence axiom 1 here is going to be satisfied because we can say every 2 pairs of sets, every pair of sets has 1 element in common. Which is the same as saying every pair of points is going to have exactly 1 line that is incident with both of them in this model. How about instance axiom 2? Is it going to be the case that given any line, any one of A, B, and C, there's at least 2 points incident with that line? Meaning given any one of these 3 letters, there's going to be 2 of these sets that that letter is in. Okay? Okay? Let's say I give you Let's say I give you L3, which give me 2 points that are going to be incident with that line. Because C is an element in this set and C is an element in that set? I would agree. Yeah, so instance axiom 2 is going to be satisfied because every letter shows up in 2 sets. meaning every line is incident with at least 2 points. In fact, exactly 2 points in this model, but exactly 2 set qualifies for at least 2. And finally, incidence axiom 3, can we find 3 points that are non-collinear out of the 3 possible points to choose from in this potential model? Elaine?
Yes.
What are your 3 points?
I think I'm gonna go with P1, P2.
Oh, interesting. So you claim that these 3 points don't have any lines passing through all 3? Why is that?
Because none of them contain, for none of the 3 lines are contained in all 3 points.
Yeah. A isn't in all 3 sets, B isn't in all 3 sets, C isn't in all 3 sets. None of these sets have these 3 sets don't all have a single element in common. If you take the intersection of all these sets, the intersection is empty, in other words, for those of you taking some set theory. So yeah, I would say this is satisfied because P1, P2, P3 are non-collinear as no one element is shared by all 3 sets. So instance axiom 1, instance axiom 2, and instance axiom 3 are all going to be satisfied. What does that tell us about this definition for lines, points, and incidents? That since all 3 instance axioms are satisfied, what does that tell us about this? About these definitions? Kate? Yes.
The model holds for instance geometry.
Yeah. In other words, this does in fact form a model for instance geometry. It forms a model because the instance axioms are all satisfied by this set of definitions. Instance geometry model as all instance axioms are satisfied. Any questions or comments about this model?
It just is really funny that we just switch the definition for line and point, basically.
Yeah,
it still
do.
works.
It still works if we switch the definition for lines and points, and incidents we just do a small little flip-flop for it.
It seems like there's not a distinction between line and point proper. It's just kind of however you define them.
However you define them. Yeah, well, we can always twist our definitions in whichever way we want to give us a different model. If I really wanted to be cheeky, I could define a new model, model 5, that's say the same as model 4, except the lines are not going to be the letters A, B, and C anymore. They're going to be the letters D, E, and F. That would also give us a model. Where literally all I've done is rename the lines, but it still would give us a model. And you can always do cheeky things to get from one model to another model in that way. But there's a reason for this cheekiness, which we'll get to in a second. Any other questions or comments? Katie?
This is kind of like 2 lines determine a point, right? Like the lines are all, if they all intersect.
Hey, how about that? The lines all intersect. What does it mean for 2 lines to intersect?
Well, they're incident at a point, I guess.
They're incident at the same point. So like L1 and L2 intersect because there's a point in common with both lines. In other words, these 2 letters are shared in a set. Yeah, that's a good way to think about it. 2 lines, we're sort of going from 2 points determine a line to 2 lines determine a point, But in a way, that incidence axiom 1 is still satisfied that there is a unique line going between every pair of points that happened because of how we constructed, even though the intuition is even less there in terms of points defining lines versus lines defining points, so to speak. I would agree with that. Okay, so here is my challenge to you. We have 4 models for instance geometry. 2 of these are secretly the same model in disguise. In other words, they're mathematically the same. They have all the same properties. They all, the only thing that's changed is a little bit of a twist in terms of how stuff was defined. I'm going to give you all a couple minutes to think about which of these 2 models do you think are secretly mathematically the same model? Were you going to answer the question?
Yeah.
Okay, well, hold your thoughts for just a second. And think about it for a minute. Which of these 2 models feel the most similar to you? And once you think you have an answer, share with your neighbors. I think what you were asking is very relevant to this question.
Oh, I know. Because at school, if you wanted to show it, you could just write out all the points and lines.
Yeah.
And then pair them up like once you make a function.
Sounds like things are quieting down. Anyone want to take a stab as to which 2 models they think are the most similar to each other? The ones that are mathematically the same? Look, you were going to say something earlier, so I'll let you do it.
Model 2 and Model 4 because everything holds exactly the only thing that changes is whether you would say at certain points whether they're concurrent or collinear, but otherwise everything is the same.
So like points and lines have swapped, so like basically the definitions of concurrent and collinearity have swapped, but everything else is the same, so you think models 2 and 4?
Yes.
Jared, what were you going to say?
Oh, I was also going to say that, yeah. They seem pretty isomorphic.
Everyone think models 2 and 4? You did. No one said models 2 and 3? Which are the exact same except for another letter? Jared?
You spoiled the surprise by telling us about the fifth postulate holding in one without the other last time.
Oh, gadzooks! The parallel postulate, the Euclidean parallel postulate, it held in Model 3, but it didn't hold in Model 2. That sounds like a significant difference between these 2 models. Good job, you didn't fall for the trick of saying models 2 and 3. So, there you are absolutely correct. Model 2 and Model 4, and Jack is sort of alluding to what you said earlier, are in fact mathematically the same model. Even if they look different, they have a little bit of a redressing up in terms of swapping definitions for points, lines, and how incidence works. Model 2 and Model 4 are mathematically the same. And what that means when we say that these are mathematically the same is that any interesting property that holds true in one must hold true in the other. And ditto, if any interesting property is false in one, it must be false in the other. So, did anybody think of an interesting property that held true in Model 2 that's going to hold true in Model 4? Jared already said it, but Nick?
The parallel postulate doesn't work.
The parallel postulate doesn't work. Gadzooks. The parallel postulate worked in Model 1 and Model 3. It didn't work in Model 2. And for pretty much the same reasoning, the parallel postulate is not going to work in Model 4. E.g., parallel postulate is false in Models 2 and 4. Since these models are mathematically the same, what's false in one must be false in the other.
What do you mean by interesting?
Ah, that is a very vague word. So here's a question. Do you think that this is an interesting property? Property. Same prop as proposition. There exist exactly 3 points. Property. This can be property 1, this can be property 2. Lines are all letters. Which of these do you think is more interesting mathematically? In other words, which of these properties is actually telling us more about how our model sort of behaves? Right?
Property one,
What's that?
because property two is just a naming thing, it doesn't really have anything to do with math. Property one says something about the number of items that are in.
So property 2, in other words, just kind of comes from a matter of labeling. How do we refer to points and lines? Whereas property 1 is actually telling us something more mathematically unique, which is there exist 3 points. No matter how you label those points or lines, whether by letters or by sets or by, I don't know, emojis, if you're feeling really cheeky, the fact that there exists 3 points in that model isn't going to be affected by how you label each of them. Whereas property 2, lines are all letters, it's not really an interesting property because it's not interesting in the sense that it only refers to the labeling of how do you refer to these things, not referring to how do they interact with each other, how many are there, how are they going to be something that's going to determine other interesting properties in some sort of way. So I'm purposely not defining the word interesting because it's very vague, and I recognize that. But ultimately, I would say interesting means something that's not just referential to how we label them, something that tells us about how do different types of points and lines, etc., interact with each other in a way. Interesting. Lame. So thus, when we say models 2 and 4 are mathematically the same, this interesting property, property 1, that there exist exactly 3 points, I would say that's an interesting property that they both share. Which, since it's an interesting property, those 2 models either better both share them or both not share them, which they both share. It's true that if property 2 only holds for model 4 as opposed to model 2, but since that's not an interesting property in the sense that it only comes down to a matter of labeling, I would say that that's not something that has to necessarily hold true for these 2 models to be mathematically the same. Any questions or comments about that? It's a good question today. If you hadn't asked it, I was going to ask it myself. Jared,
How would you prove this from a logical standpoint?
we'll get to that on the next page.
Okay, cool.
Why you go through and check every single potential interesting properties, of course.
Yeah.
Does that sound reasonable?
Maybe. I was thinking we could come up with a bijective function. Oh, okay.
So, Derek asked the question, okay, that's all well and good, Dr. Gerstle, but it's not really very feasible actually to go through and check all interesting properties because technically there's infinitely many you could come up with. Like, I don't know, interesting mathematical property 1. These two models do not have 17,562 points. Interesting property number 2.
There are not 5,667 lines.
There do not exist, yeah, listen, interesting property number 3. In both models, there does not exist a set of collinear lines, or collinear points, or concurrent lines, however you want to refer to it. You could be really, really cheeky and come up with infinitely many interesting mathematical properties you could in theory check. So, the way that we're actually going to prove that models 2 and 4 are, in fact, mathematically the same is through this idea of isomorphism, where we're going to find a function going from the points and lines of one model to the points and lines of another model. So I'm going to skip 2 pages ahead in the packet. I'll let you all think about how the propositions hold for model 4. And we're going to go to one where it says 2 different models are isomorphic, following the first. So here's what we need. So here's the more precise definition. 2 models, M1 and M2, are isomorphic if, first of all, there exists a one-to-one correspondence from the points of one to the points of the other. And I'll talk about what does one-to-one correspondence mean in just a second. Second condition, same thing, from the lines of one to the lines of the other. And the third condition that needs to be satisfied is that these one-to-one correspondences, which are going to be functions, let's say these maps satisfy if, let's say P1 corresponds to P2 and L1 corresponds to L2, then P1 is incident to L1 if and only if P2 is incident to L2. So I recognize that there's a lot of terms in there that I have not defined. So, and yes, Jared, you can replace the word one-to-one correspondence with bijection if you want. I'm using the terminology that's in the book. But let's go through and talk about what does all of this actually mean for us. So what this means is that we have some way of going from the point, and we have a function that's going to take in points in one model and spit out points in the other model, and another function that's going to take the lines in one model and spit out the lines in the other model, and it's going to do it in a way so that incidence inherently kind of works, quote, the same, unquote, in both models. So let's write out all the points and all the lines in models 2 and 4 to see what we mean by this. So, Model 2, in Model 2, the points were letters and the lines were the sets. So I'm going to write out P1 equals A, P2 equals B, P3 equals C. L1 was the set containing A and B. L2 is the set containing A and C. And L3 is the set containing B and C. On the other hand, in Model 4, it's the same thing but kind of opposite. We can think about here as, call it P1 hat for now. It's going to be the set containing B and C. P2 hat is going to be the set containing A and C. P3 hat is going to be the set containing A and B. And down here, L1 is going to be C, L2 is going to be B, and L3 is going to be A. So we've written out all of the points and the lines of both models. And what we mean when we say one-to-one correspondence, I mean a function from one to the other So I want a function that's going to take in points in, say, Model 2, and is going to spit out points in Model 4. And similarly, we need another function that's going to take as inputs lines in Model 1 and spit out lines in Model 4. And one-to-one correspondence is going to correspond, unintentional pun, is going to mean that every point in M4 and every line in M4 is going to get mapped to by exactly one element of the points or lines in M2. So it's a function from one to the other where each point / line in M4 is mapped to by exactly one point / line in M2. So let's see if we can do this. So I want to come up with a way to map, to take a function that's going to take in a point in M2 and spit it out with a point in M4. Elaine, I know you've seen these before. So what would be a way that we could define a function that takes as inputs points in M2 and has outputs points in M4 and does it in a one-to-one correspondence sort of way?
Can I just do it point by point?
I think you would have to.
Okay. I mean, I would want to do P1 to P3, P2 to P1, and P3 to P2, I think.
Aha! First of all, is this a one-to-one correspondence? It's a one-to-one correspondence because every point here in M4 gets mapped to exactly once. There's one arrow going to each of them from a point coming from M2. If we had, say, two arrows, say an arrow from P1 to P1 hat and an arrow from P2 to P1 hat, that would not be a one-to-one correspondence because you'd have multiple things mapping to P1 hat, which you don't want. That being said, Elaine, I don't like your choice of one-to-one correspondence. I very much tried to help you out here by setting it up in the way I want.
I didn't like the way you said it. I'm confused.
And
I'm uncomfortable.
why did it make you uncomfortable?
because you have, A goes to one without A.
Oh, but
You put them upside down.
That's how you tell.
Oh, but there is a method to my
I
madness.
figured, but.
And the reason why, Elaine, yours works, it works perfectly fine for property number 1. It just so happens that what you came up with isn't gonna work when you get to property 3. So here is, what?
Boo.
Is boo-hoo. So here is my proposed one-to-one correspondence.
So boring.
So you can think about each of these arrows as being like a function, that there is corresponding to a functional output. So you can think about, say, these 3 points in M4 as being f of P1, f of P2, f of P3. In other words, the output to a function f that takes in points from M2 and spits out points in M4. And we can similarly say the same thing about having lines in Model 2 mapped to lines in Model 4. And think about f as, technically I'm cheating here by having the same map refer to points and lines. But think about f as being a map that takes in points from M2 to points in M4 and lines in M2 to lines in M4, and does it in a way that every point and line in M4 gets mapped to by exactly one of the same type of object in M2. So points in M4 get mapped to by points in M2, lines in M4 get mapped to by lines in M2. And here's the kicker. Condition number 3. These maps satisfy that if P1 maps to P2 and L1 maps to L2, then P1 is incident to L1 if and only if P2 is incident to L2. So let's, we're done with this part. What's this? So, all right, Elaine, would you like to redeem yourself?
Maybe.
All right. So, P1. Which lines in M2 is P1 going to be incident to?
L1 and L2.
It's going to be incident to L1 because A is an element in this set. It's going to be incident to L2. How about L3?
No.
So P1 is going to be incident to L1 and L2. P1 is not going to be incident to L3. Now let's ask something on the flip side. Which lines in M4 is f of P1 going to be incident to? Jared?
L1 and L2, but not L3.
Whoa. You're saying they're going to be incident to these things?
Oh, no, wait, are there hats on those?
Call them f of L1.
Okay, F of L1 and F of L2, but not F of L3.
Aha! So you're saying that the set here, it is incident to this point is incident to these 2 lines, but not this third one? Let's write that out. So f of P1 is going to be incident to f of L1 and f of L2, but f of P1 is not incident to f of L3? That's interesting. What's interesting about this? Does anybody see sort of something going on here? P1 is incident to L1 and L2, but not L3. F of P1 is going to be incident to f of L1 and f of L2, but not f of L3. condition number 3 here essentially says that points and lines, how they behave in the first model with regards to incidence. If you have a point and a line that are incident in the first model, then whatever our maps F map these points and lines to in the second model, say F of P1 and F of L1, are still going to have to be incident. Points and lines that are incident in the first model have to map to points and lines that are incident in the second model. And similarly, points and lines that are not incident in the first model, say P1 and L3, these were not incident, are going to map to things in the second model that are not incident. F of P1 is not incident to F of L3. So when we say that these maps, the Fs that we came up with on the left-hand board, satisfy that if P1 corresponds to P2 and L1 corresponds to L2, meaning P1 maps to P2 and L1 maps to L2, then the points and lines that are incident in the first model, if and only if, the points and lines that they map to in the second model are also incident. So when you think if and only if, I want you to be thinking it works both ways. If two things are incident here, then they have to be incident in the second place, in the second model. And if two things are incident in the second model, then the things that map to them in the first model are also going to have to be incident. And that light is why I didn't like your map that you chose. It worked perfectly fine as a one-to-one correspondence from the points of the first model to the points of the second model. But I knew that unless we were very, very creative in how we came up with our second, the maps between lines, it wasn't going to satisfy property 3 here. That's why I shut your idea down.
Bummer.
Quite. What questions or comments do you have on this?
Does it have to go the other way too? Like if you I guess you could do inverse function or something.
Yep. Yeah, the idea of one-to-one correspondence, part of that is you can always invert it and have an inverse function. So in this case, if P1 maps to F of P1, you could have an inverse function that just sends this point back to that point, this point back to that point, this point back to that point, ditto with the lines, and just have it work as the exact same function but working backwards. And part of having a one-to-one correspondence is that you have that.
Is there, I know that for functions there's also the on-to requirement. Is that necessary here?
Yes, one-to-one correspondence is another way of saying function that is one-to-one and onto.
Okay.
Onto, one-to-one means no input has multiple things mapping to it. Or nothing in the second set has multiple things mapping to it. Onto means everything in the second set has to have at least one thing mapping to it. So if you have one-to-one correspondence, one-to-one and onto, that says given any point here, you have to have at most one thing mapping to it and at least one thing mapping to it. That's a more formal way of saying everything here has to have exactly one thing from the first model that's going to map to it. Dr. Gerson, this is a horribly complicated definition. Why are we doing this? Steph, I can see you nodding along with that. The idea here, and this is a common one in math, is coming up with a formal way to say that two different types of mathematical objects are, quote, the same, unquote. Meaning they're all the interesting properties that one shares, the other will share, and vice versa. So, this, by the way, tells us that M2 and M4 are isomorphic. The fact that we can find maps between the points and lines that satisfy this property. And we can write that out and symbolically you can write that out as M2 and the little squiggle over an equal sign, M4. That's a symbolic way of saying M2 is isomorphic to M4. This is a common idea in math, where two things in a mathematical sense are isomorphic if they behave the same way. if they have all the same properties to them, even if they look different. And in general, whenever you have the idea of isomorphic, you always have something going on where there's a one-to-one correspondence between the objects in one and the objects in another. It's like in abstract algebra, you could have two groups that are isomorphic, saying you have a one-to-one correspondence between elements of one and elements of the other. If you take topology, you replace the word isomorphism with homeomorphism. If you haven't taken topology, which I'm guessing most of you haven't since it's been almost 2 years, take it this spring. Homeomorphism basically says two types of objects are mathematically the same, like a coffee cup and a donut. You've ever heard the joke that to a mathematician a coffee cup and a donut are the same? Basically saying you could take a donut and mold it in your hands and stretch it and poke it and tug at it, but doing everything in a continuous way, not a way that breaks anything. You can mold a coffee cup made out of Play-Doh into a donut, or vice versa. That's, in topology, you would say that they're homeomorphic to each other, that they're mathematically the same because you can mold and fold one into the other, and to a topologist, a coffee cup and a donut have all the same interesting properties in common. In abstract algebra, you say like two groups or two rings are isomorphic. In geometry, you can say that two different geometric models are isomorphic by having this one-to-one correspondence that preserves the structure, such that the structure in the first model behaves the same way as the structure in the second model. Whereby preserving the structure, I mean condition number 3 here, that points and lines that are incident in the first model have to map to things that are incident or not incident as need be in the second model. It's a heavy idea, but I think it's a really cool one, which is why I wanted to spend a day to talk about this. Okay, question. I claim M2 and M3 are not isomorphic. Remember, M2 is M3 is the model that's the same as M2 except it has 4 points instead of 3 points, thus more lines to work with as well. How do we know that M2 and M3 are not isomorphic? Yeah, somebody.
There's no way to do a one-to-one correspondence between their points or their lines, because there's only 3 points and there's 4 points, so you can't line it up so that each point in M3 gets mapped to by exactly 1 point in M2.
Yeah, if we were to just look at, say, the points, let alone the lines in between these two models, here, if we look at the points in M2, they'll be A, B, C. In M3, we'll get A, B, C, D. Is there a way that we can map the points to in M2 to points in M3 so that everything in M3 gets mapped to exactly once? Rebecca? Why not? Yeah, Zeus. We could try our hardest and say A goes there, I don't know, B goes here, I'm sure C can map to itself, why not? But there's always going to be something in the second model that can't get mapped to. There's just not enough points in the first model to have every point in the second model mapped to exactly once. And similarly, if we tried to go from the points of M3 to the points of M2, we couldn't do it in a one-to-one correspondence because something would have to get mapped to multiple times. So that's a way that you can say these two models are not isomorphic. It's impossible to form a one-to-one correspondence between their points. And thus, if you have two models that are isomorphic, they have to have the same number of points, as well as the same number of lines by similar reasoning. So, two models isomorphic means they behave mathematically the same, otherwise they do not. So for instance, none of these models we talked about in the last couple days are isomorphic to the traditional model because, none. How many points and lines are there in the traditional Euclidean geometry? Infinitely many. No way to form a one-to-one correspondence between infinitely many points and say 3 or 4 points. That's one way you can quickly say traditional model is not isomorphic to any of the other ones we've talked about thus far. And that can do it for instance geometry. When we come back on Monday, we're going to start talking about betweenness geometry and add in some new axioms and we'll have a new undefined term, which is what it means for one point to be between 2 other points. Hope y'all have a good rest of your, I hope y'all have a good weekend. I'll see y'all on Monday.